Hello and welcome to this video on how to debug your custom logic design on Amazon F1 instances using the Xilinx UltraScale Plus FPGAs. In this presentation, I'll walk you through the various debug cores that are available as part of the Xilinx Vivado IP catalog. I will also go through the steps required to customize and instantiate these debug cores into your custom logic design. I will then go through the debug setup in the design that is being used for the demo. I'll also go through some details of how to connect to this design running on F1 using the virtual JTAG server. I will then demonstrate the steps required to start the debug servers on the Amazon F1 instance, to connect to it using a local Vivado instance running on your local machine, and interact with the debug cores, trigger the ILAs, capture the data, and monitor AXI events. The Xilinx Vivado IP catalog offers a variety of debug cores depending on your design requirements. A couple of widely used debug cores are the ILA and VIO cores. The ILA, which is the Integrated Logic Analyzer core, allows you to perform in-system debugging of your custom logic designs as it is running on the F1 instance. This feature should be used when there is a need to monitor signals in the design, to trigger on specific hardware events on those signals, and to capture data at system speeds. This debug core needs to be instantiated in the custom logic RTL code. The Virtual Input-Output Debug core, or the VIO, can be used to both monitor as well as drive internal FPGA signals in real time in your custom logic design. In the absence of physical access to the target hardware, you can use this feature to drive and monitor signals that are present in the hardware, which is your F1 instance. This debug core needs to be instantiated in the custom logic RTL code. There are 3 steps required to add the debug cores to your custom logic design. Step 1 is to customize and generate the debug bridge IP using the IP catalog in Vivado. You need to set the debug bridge IP in the bscan to debug hub mode. Step 2 is to determine the number and type of debug cores that you want to add to your custom logic. You can then customize and generate the required number of cores using the IP catalog in Vivado. Step 3 is to instantiate the debug bridge and the debug cores in your custom logic RTL design. For the purposes of this video, we have modified the Amazon DMA example design. This design reads in data from the DMA and writes it to the DDR memory in the custom logic space, and it ensures that the data copied is correct and matches the data that was supplied earlier. In a typical custom logic design, you will add your user logic to the CL region and connect it to the boundary IOs. Now, if you decide that you want to debug your design, now is the point at which you would add the debug IPs to the CL region and you would connect it to the design signals. We recommend adding these debug cores early on in your design cycle. Now is also a very good time where you should be adding the debug bridge IP to your design. We use the Xilinx virtual cable protocol to communicate with the design under test on the F1 instance. The Xilinx Virtual Protocol is a TCP/IP-based protocol which acts like a JTAG cable without requiring a physical JTAG connection. So XVC helps when the design under test is on a board that is hard to reach, that is not easily accessible, there is no direct access to the physical JTAG pins, or if you need to remotely debug the design when it's deployed in the field, as is the case with our F1 instance. For the purposes of this video, we have already built the design and created the Amazon FPGA image, or the AFI. For more details on how this is done, please watch the Introduction to F1 video. So once this design AFI is programmed onto the F1 instance, how do we debug the design? We need to launch the virtual JTAG server. This is an AWS command. And this server enables communication between the design under test and the PCIe module. We should also launch the hardware server on the F1 instance. The hardware server is available as part of the Amazon Web Service HDK release. Now that you have both the hardware server and the virtual JTAG server running, you can now invoke Vivado. You can either invoke Vivado on the local F1 instance, or you can invoke Vivado on a remote machine, such as your laptop or your Linux machine. You will then open a connection between Vivado, the hardware server, and the virtual JTAG server using TCP/IP. Now you can use the Vivado GUI to interact with the debug course. I'll give you a quick demo of using Vivado on my laptop to debug the design running on the F1 instance. The steps are as follows. I'll connect to the F1 instance, load the AFI, and load the DMA driver. In the interest of time, I have already performed these steps. I'll then show you how to invoke the virtual JTAG XVC server on the F1 instance, and then also invoke the hardware server on the F1 instance. I will then open Vivado Lab on my local laptop. I'll connect to the target on the F1 instance using the hardware server. I'll interact with the debug course, trigger the ILA, and capture the debug data. I'll also visualize certain AXI events and transactions. At this point, I already logged on to my EC2 management console, and I noted down the private and the public IP address of my F1 instance. I already logged on to my F1 instance using SSH. I've already loaded the AFI and the Linux kernel driver required for this DMA design. Let's run the Vivado hardware server now. Let's run it in the background. Note the IP address and the port that it's using. It's port 3121, and the IP address is the private IP address of the F1 instance. Next, let's run the virtual JTAG XVC server. Note the TCP port number being used, 10201. Let's use SSH to log on to the Amazon F1 instance in another terminal window. Note that in addition to just logging on, we're also using port forwarding. We're port forwarding the port 3121 on the F1 private IP address using the SSH-L option. The reason we do that is because the hardware server used the port 3121, and we will use this port to communicate with Vivado. I have Vivado Lab Edition installed locally on my laptop. Let's create a new project. Next, we open a new target. Let's specify the name of the machine used in the SSH port forwarding. Let's also specify the port 3121 to connect to the hardware server. So now we have connected to the hardware server running in the F1 instance. Let's now connect to the Xilinx virtual cable target. It's local to the hardware server, and it's at port 10201. Now you can see the debug cores in the design, the VIO and the two ILA cores. Note, however, that the waveform window doesn't show any debug signals, and the trigger setup window indicates that we need to provide a probes file. Go to the debug bridge component in the hardware window. Note the probe's file property is empty. Let's click on the Browse button and browse to the AWS checkpoint directory. This is where we built our custom logic design. In addition to creating a tar file to create the AFI, there is also an LTX file that is generated. Select this LTX file. In cases where you build the custom logic design on the Amazon F1 instance, use the scp command to copy the LTX file from the F1 instance back into your local directory. Once this file is provided, the waveform window is now populated with the signals that are being monitored. Let's now look at the VIO dashboard. This VIO core is monitoring signals output from the counter in the custom logic design. In addition, it can also drive the counter using the enable signal. Let's right-click on the enable and clear signals and drive them as a toggle button. Let's toggle the clear signal to clear the counter, and let's enable the counter. Note, the counter has started counting and the values are being tracked. Now let's go to the ILA dashboard, which is monitoring this counter. Let's trigger on the falling edge of the enable signal. Let's move to the trigger settings window. We'll change the trigger position in the window to 512. Let's arm the ILA. If you look at the status of the ILA, it is waiting for the trigger. Now let's use the VIO to trigger the ILA. You can use the dashboard options to go and include the VIO window inside of your ILA dashboard. Now let's select the enable signal in the VIO. On toggling the signal, we now trigger the ILA. We see that the ILA status has gone from waiting to full. It has loaded the data in the waveform window. When we look at the waveform window, we see that the counter was counting up until the enable signal was toggled. Now let's transition to the ILA monitoring the two AXI interfaces from the DMA to the DDR. This is the AXI slave interface that is coming from the shell region. The other one here is the interface to the DDR controller in the custom logic region. So basically, write transactions occur from the DMA into the custom logic region, and it's written to the DDRs in the custom logic region. Conversely, a write transaction occurs when the data in the DDR is read back in the opposite direction. At this point, I want to show you the trigger condition setup. We want to trigger on any read or write transactions in any of these two interfaces. So let's click on the plus button. Let's add the read and write control signals for both these interfaces. We change the trigger value of these signals to a 1. Let's also change the trigger condition to a global OR, where the ILA will trigger if any of these signal values are a 1. I'm also setting the trigger position in the window to 50. Now I'll go ahead and arm the trigger. Note the status change of the ILA. It's waiting for a trigger. Let's go ahead and trigger it. Let's go back to our F1 window and let's run the example. Look, now the status is full. It's uploading the data. We have triggered on a write event. We can zoom in on the event and we can see that there are data beats associated with these transactions. There are 4 data beats, and you can see that after the write, it takes a few clock cycles for it to show up in the DDR. Once all the data is written, you get a write response from the DDR controller. And this response is passed back to the PCIe slave through the interconnect, which signifies that the write transaction is done. So now you can actually see the data flowing through the system, including the timing, which is how long it's taking for the data to get from the DMA to the DDR. You might want to debug why there are so many clock cycles between the responses. You might want to debug why there is a difference in the clock cycles between the end of the last data beat and the write response. What's taking so long and what the holdup is. These are some of the things that you can debug at this level. This concludes our demo. Thank you for watching the Xilinx Quick Take video on Introduction to Debugging Custom Logic Designs on Amazon F1 instances using Xilinx FPGAs.